Hey everyone, and welcome to this explainer. I am absolutely thrilled you're here today. We are about to embark on a pretty awesome mission. We're going to hack our way through the historically terrifying world of partial differential equations, or PDEs. Look, if you've ever felt a cold sweat just looking at a hardcore math textbook, believe me, you are in the exact right place. We're going to take the heat equation, which is basically one of the most fundamental concepts in all of engineering, and we're going to completely demystify it using the power of modern software. So let's jump right in, shall we?
To kick things off, take a look at this hilariously blunt assessment from Dr. David Kafer over at the University of Tennessee. In his engineering course materials, he freely admits that most engineers, after surviving a few brutal math classes, realize they absolutely never want to solve these massive equations analytically by hand ever again. I love this quote because it perfectly validates any math anxiety you might be bringing to the table today. It is totally okay to find this stuff daunting. Even the professors admit it's a beast.
Which brings us to Section 1, the fear of PDEs.
See, for decades, the PDE was basically the ultimate monster lurking in the syllabus. In the literal dark ages of engineering, students were forced to rely on these incredibly dense, limited analytical textbooks. Dr. Kafer actually mentions a classic one by Karslow and Jaeger called Conduction of Heat and Solids. Imagine generations of students wading through those massive books, literally crying over complex derivations, only to find they were limited to the exact specific problems the authors had already solved. But today, we are in the modern era. We get to wield numerical methods and software like MATLAB. What used to take pages and pages of agonizing calculus can now be solved, as Dr. Kafer puts it, like a piece of cake.
All right, moving on to Section 2, decoding the heat equation.
Before we can just unleash the software, we do need to decode some of that intimidating math. When you first look at the heat equation, you're usually juggling three distinct physical properties: thermal conductivity, density, and heat capacity. And honestly, that is a lot to keep track of. But we can actually combine all of them into one single, highly elegant parameter called thermal diffusivity, which we represent with the Greek letter alpha. By simply dividing thermal conductivity by the product of density and heat capacity, we strip away all that intimidation factor. We're literally reducing three complex material parameters down to just one manageable number. And all that number does is dictate how fast heat spreads through a specific material. Simple, right?
And honestly, if you look beneath all those Greek letters and partial derivative symbols, what is the heat equation really? Well, it's actually just an unsteady state energy balance. That is the whole shebang. It's basically just an accounting trick for energy. You track the heat going in, you subtract the heat going out, and what you're left with is the heat that builds up the accumulation over time, plus any heat generated internally. Once you realize it's just basic bookkeeping of thermal energy, that fear we talked about, it completely vanishes.
So that takes us to Section 3, the finite difference solution.
Now that we're no longer terrified of the equation itself, how do we actually go about solving it? Well, let me introduce you to our magic sword, the finite difference method. Dr. Kafer lays out these 5 incredibly simple, empowering steps to tackle any heat transfer problem like a modern 21st century engineer. First, you just describe your physical system in plain English. Second, you translate that into your PDE, your energy balance. Third, you punch that information right into your software. Fourth, you hit run. And fifth, you get to sit back and analyze the beautiful solution it spits out. Did you catch what's completely missing from that list? Yeah, you are not doing pages of manual integration. The software is doing all the heavy lifting for us.
But you might be wondering, how does the software actually pull that off? Well, that is exactly where the Finite Difference Method, or FDM, comes into play. I want you to think of it like a metaphorical meat cleaver. It takes this massive continuous problem, like a solid rod where the temperature changes smoothly across every microscopic point, and it just chops it up into a discrete grid. It slices the rod into tiny, manageable spatial segments, and it slices time into tiny forward steps. So instead of trying to solve for infinity, the computer just solves some basic algebra for each tiny piece of that grid, step by step, until the whole picture emerges. It is brilliant.
Next up, Section 4, setting the boundaries.
To wield this numerical sword properly, we really have to teach the software how our physical system interacts with the outside world. And there are 3 main ways we define these boundaries. First up, we have Dirichlet boundary conditions. This is for when the temperature is rigidly fixed at the edge of your system, kind of like placing the end of a rod into an infinite heat reservoir, like boiling water. Second, we have Neumann boundary conditions. Now this defines the heat flux, or the rate that heat is actually moving across the boundary. So if the end of your rod is perfectly insulated, zero heat escapes, which means the flux is zero. That is a Neumann condition. And finally, mixed boundary conditions. This is when you have heat loss to the surrounding environment. Picture a warm rod just sitting in a cool room, naturally losing heat to the air. You just tell the software which of these three applies to your edges, and you're good to go.
Now, alongside those boundary conditions on the edges, we also need to establish our starting line. Because the heat equation tracks changes over time, the computer absolutely needs to know what the temperatures were at time equals 0. We call this the initial condition. It really could be as simple as telling the software, hey, this entire aluminum rod is starting at a uniform 300 Kelvin right before we turn the heat on.
Which brings us to Section 5, MATLAB to the rescue.
Okay, so we've got our physical system, our chopped up grid, our edges, and our starting line all figured out. Now it is time to let software like MATLAB take the wheel. What makes these computational tools so incredible is that they seamlessly handle the real-world headaches that make manual math just hopelessly ugly. For example, in the real world, a material's ability to conduct heat actually changes as it gets hotter. If you tried to calculate that temperature-dependent thermal conductivity by hand, absolute nightmare. But MATLAB handles this nonlinear property effortlessly, updating the thermal conductivity in real time as the simulation chugs along.
Plus, we aren't just limited to simple one-dimensional cylinders or straight lines anymore. MATLAB actually has built-in features like PD Tool that use finite element analysis to solve heat equations for highly unusual complex 2D geometries. A really great example straight from the MathWorks documentation is modeling a heated rectangular block that has an arbitrary rectangular cavity cut right out of the center. If you were doing analytical math, this geometry would be devastatingly hard to solve. But with the software, it's literally just a few clicks to draw the shape, set those boundaries we talked about, and watch the heat flow around the cavity.
Finally, let's look at Section 6, Real-World Thermal Modeling. Let's take everything we've learned so far and see exactly why this math matters out in the wild. Check out this research from the Johannes Gutenberg University in Mainz, Germany. Researchers and students over there, like BJP Kaus, are applying these exact 1D transient heat equations not just to little lab experiments, but to massive high-stakes geological models. It really shows the incredible predictive power of the finite difference method when you apply it to the natural world.
In fact, here is the exact problem they pose. I want you to imagine a massive underground intrusion of a basaltic magma dike. This liquid rock is sitting at a blistering 1200 degrees Celsius, and it violently forces its way into cooler, surrounding country rock that is only at, say, 300 degrees. So, how long does it take for that magma to cool down? What happens to the surrounding rock? This is an extreme, real-world scenario that you simply cannot guess the answer to by eyeballing it. It absolutely must be solved using our new finite difference tools.
Well, by setting up those initial conditions, 1200 degrees for the magma, 300 for the rock, and letting the software do its thing, the numerical models reveal something truly amazing. They visually map out the exact danger zone, calculating the maximum temperature that the surrounding rock experiences. They can even calculate the exact width of what geologists call the metamorphic aureole. This is the precise area where the heat exceeds 600 degrees Celsius, literally baking the surrounding shale and permanently transforming it into a completely new, rock-hard material called hornfels. We are quite literally mapping geologic history just by simulating heat transfer.
And wild as it is, geology is really just the tip of the iceberg here. As highlighted in the Wired White resources and Dr. Keffer's project requirements, mastering this one mathematical tool unlocks the entire engineering universe for you. You can model the cooling of microelectronics using advanced nanofluids. You can simulate the thermal aging of lithium-ion batteries to prevent them from, catching fire. You can even adapt these exact same tools for quantum mechanics to study wave packet dynamics. Honestly, from calculating the critical insulation thickness on a steam pipe to testing how a 2D plate reacts to oscillating temperatures, the applications are truly endless.
So look at what we've done today. We've broken down that initial fear of PDEs, we've uncovered the simple energy balance hiding beneath the heat equation, and we've seen firsthand how software like MATLAB turns impossible analytical problems into elegant numerical solutions. You officially have the magic sword, so the only question left for you is, what complex system are you going to model first? Thank you so much for joining me in this explainer. Keep learning, keep hacking those equations, and I'll see you next time.